Okay, so our integration by parts lesson part 2. We're actually going to go back to our first example. Okay, and I'm going to show you a tabular shortcut. Now, just because we can do a table shortcut doesn't mean that we can ignore the actual technique of integration by parts. There's going to be problems that the shortcut does not work for or that does not apply to, so you need to be able to do it both ways, but the shortcut is definitely a time saver, and when it comes time for a test, I will tell you when you can use one or the other. Okay, so when we're doing a shortcut, we're still going to start by identifying U and dV, but instead of just doing it, we're going to do it in a table form. Okay, and you're still going to pick your U and your dV the way that you've been picking your U and dV. Okay, you want to pick your U so that when you take the derivative, it's not going to, well, the bigger thing is when you're picking your dV. When you integrate it, it's not going to get any more complicated. So we're still going to pick cosine x for my dV. Okay, I don't really need to keep the dx in there, but, and then for my U is just going to be my x. Okay, and what I'm going to do is on the u side, I'm going to take a derivative down until I get to 0. Okay, so the derivative x is 1. The derivative of 1 is 0. That means I'm done with my derivatives. Okay, now on the dv side, I'm going to take as many integrals to fill in my chart so that it matches up. I have the same number of rows as my u side has. Okay, so u, I take the derivative down to 0. My dv, I integrate until I match up with my u side. So the antiderivative of cosine x is negative sine x, and the antiderivative of negative sine x is negative cosine x. Actually, I got those signs wrong. I apologize, I was taking derivatives. So the derivative of cosine x is, I'm sorry, the antiderivative of cosine x is sine x, and the antiderivative of sine x is negative cosine x. Okay, and then what we're going to do is we're going to alternate signs, always starting with a positive to match the number of rows. So I'm going to do a plus, a minus, a plus. Okay, if I had more rows, I would continue plus, minus, until I reached the bottom row. Okay, the very last thing is that I'm going to look at the diagonals. Okay, so I'm going to be pairing up diagonals here. All right, and I'm going to read the diagonals, and that's going to be my answer. Okay, so I have x times sine x, and I have a minus 1 times a negative cosine x, which is plus cosine x, and I add a plus c. Okay, so we love our tabular technique. It gives us the exact same answer as that long way did, and this is going to be really, really helpful when I have higher powers of x floating around my problems. Okay, let's look at another one. Okay, this is number 3. Okay, since we had 1 and 2 on the previous slides and the previous lesson, and I just redid number 1 and tabular data. So this is number 3, the integral of x to the 4th sine x dx. Now what I want you guys to visualize on this, well, let's start by picking our u and our dv, and then we'll see what happens. Okay, so our dv is our main focus. I want to have my function that's not going to get any more complicated when I integrate it. So pause, think about it, pick your u and your dv, and come back to me. Okay, so our dv, the one that's not going to get any more complicated if I integrate it, is my sine x. Okay, and our u, which is going to get simpler when I take its derivative, is going to be x to the 4th. Okay, and it's going to get simpler because it's going to, when I take the derivative, I'm going to end up with an x cubed, which is a less complicated function than if I were to integrate x to the 4th, I'd end up with an x to the 5th, which is a more complicated function. I do not want more complicated functions. Okay, so I want you to kind of visualize what this would be if I were doing it the long way. If I did my uv minus the integral of v du, I would end up with an integral that had an x cubed sine x in it, which would for sure be better. It wouldn't be any worse, but it wouldn't be fixed. And it would require me to do integration by parts again, and I would have a u as an x cubed and a dv that had another trig term in it. Let's not go into the logistics of what that trig term would be. And when I did my integration by parts, I'd end up with an integral that had an x squared and a trig term in it, which would be better. But I still wouldn't be in the clear, so I'd have to do integration by parts again. It would end me with a x times a trig, and then I would do integration by parts again, and that would leave me with a plain old trig integral. So our tabular method is going to be much better than doing those 5 integrals. So again, on the u side, you're taking the derivative until you get down to 0. So the derivative of x to the 4th is 4x cubed. Okay, pause, come back to me if you need to. The derivative of 4x cubed is going to be 12 x squared. The derivative of 12x squared is 24x. The derivative of 24x is 24, and the derivative of 24 is 0. Okay, I'm going to integrate on the sine side. Okay, so pause and come back to me. The integral of sine is negative cosine. The integral of negative cosine is negative sine. The integral of negative sine is positive cosine. The integral of positive cosine is positive sine. And then the integral of positive sine is negative cosine. Okay, the last thing to do is to alternate signs down this side, starting with a positive always. So plus, minus, plus, minus, plus, minus. And my last thing to do is to consider the diagonals. So I'm going to read diagonally. Okay, so you're looking at all these steps diagonally, and then I'm going to multiply those through to get my answer. Okay, and it's going to be a long one. All right, so I have an x to the fourth times a negative cosine x. That's negative x to the fourth cosine x. Okay, and then I have a minus 4x cubed times a minus sine x. That's going to be a plus 4x cubed sine x, sorry. And then I have a 12x squared times a cosine x. That's going to be plus 12x squared cosine x. Okay, and then next is minus 24x times sine x. Minus 24x times sine x. And then I have a 24 times negative cosine x, so minus 24 cosine x. And I can't forget my plus c at the end. Okay. All right, so the tabular method, I don't know if you guys want to try to do this the long way and do it for a step or two to see that the integrals are in fact getting better, but it's a long process, or if you're just content with the tabs. But this is for sure better when you're doing the tabular method. Okay, let's look at another one. Okay, so now a very big moment for us, the integral of natural log of t dt. Okay, so we're actually going to see that our tabular method is not going to work for this. Okay, and part of the problem is that we'll never get a u to go down to 0. Okay, so we're not going to be doing tabular method on this. We need a long way. The other thing that I want you to realize is that we've never been able to integrate natural log. We've been able to take its derivative. The derivative of natural log of t is 1 over t, but we have no function when you integrate it. I'm sorry, we don't have a function whose derivative is natural log. Okay, so I don't know what the antiderivative of natural log is, and we're going to be able to fix that doing integration by parts. So we're going to do it the old-fashioned way, the long way. So go ahead and pick your u and your dv. Okay, and you can pause and come back to me. I want you to really think about this one. Okay, so if you started by picking your dv being natural log of t dt, you're going to see that when you try to integrate this, you're going to end up in the same initial problem that you have. I have the integral of natural log of t dt. Okay, so my only other option is to put that natural log of t in here for u. Okay, and then if this is my u, then the only thing that's left for my dv is this dt over here. Okay, and here is an exception to our initial rules that we set, that when I go to integrate these, or I'm sorry, when I go to integrate that dv side to get du and v. So go ahead and find me du and v. Okay, you can pause and come back. Okay, the du, if u is natural log of t, then du would be 1 over t dt. And if my dv is dt, then if I integrate both sides, I'm integrating 1 dt, I'm going to get a t. Okay, so this is my exception that when I integrate, my v is more complicated, but we're going to see that it's all going to work itself out. So go ahead and pause and do uv minus the integral of v du, and then come back to me. Okay, so if I do uv, I'm going to have natural log of t times t. I'm going to write that as t times the natural log of t, minus the integral of v du, so I have t times 1 over t dt. Okay, and you'll see what happens with this lovely little integral is that these can simplify. So I'm actually going to have t times the natural log of t minus the integral of t times 1 over t is just 1 dt. Okay, and now that's a wonderful little integral. So I'm going to have t times natural log of t minus the integral of 1 dt is just going to be a t, and I need my constant of integration plus c. Okay, so as it turns out, the integral of natural log of t is t natural log t minus t plus c. Okay, and just as a general piece of advice is when you have an integration by parts problem where we have a natural log involved, your natural log is always going to show up in your u, okay, and your dv will be whatever's left, okay, even if that seems to make a more complicated function. All right, let's look at one more. Okay, so just to show you a nice variety, this is our last type that we're going to cover that you'll see show up on AP. It's the integral of e to the x sine x dx. And one of the things that's unique about this one is that we have two functions that are cyclic in nature when we're going to take derivatives and integrals. Okay, the derivative e to the x is e to the x, the antiderivative e to the x is e to the x. The integral of sine is negative cosine. The integral of cosine is sine. When I integrate either or take the derivative of either of those functions, they get no better, no worse. They just stay the same. Okay. So here's a problem where, again, tables aren't going to work for us because my derivative will never get down to 0. But if we do it the long way, it really doesn't matter what we pick for u and dv. So you can pick whatever you want. I'm going to do here's my rule. If either of these, either the exponential or the trig ones are composites, I'll pick that for my u because I'd rather have to do chain rule on a derivative than a u substitution on an integral. But other than that, I'll pick my u to be my trig function, okay, just because I'm better at remembering my signage, my positives and my negatives, when I'm taking derivatives of trig versus when I'm integrating them. So I'm going to pick u to be sine x and dv to be e to the x dx. Okay, so go ahead and pause and find me du and v, and then come back to me. So if u is sine x, du is cosine x dx. Okay, and if dv is e to the x dx, when I integrate to find v, I'm going to get e to the x. Okay, and I'm going to do uv minus the integral of v du. So I'll have uv, e to the x times sine x, I'm going to put my trig at the end, minus the integral of v du, so e to the x times cosine x dx. Okay, so one of the things that we should notice is that our integral isn't any better, but it's also not any worse. So what we have here is fine, even though it doesn't feel like a resounding success. But what I can do when I have an integral that's still an issue, it's an integration by parts form, I'm going to do another integration by parts on it. Okay, so I'm just looking at this right now. I'm going to do another integration by parts on this. I need to be consistent in this problem. So initially it didn't matter which you picked for your trig and which you picked for your exponential, but now it matters that I picked trig to begin with, I got to continue to pick a trig. So I'm going to let u equal cosine x, and my dv would be still my exponential e to the x dx. Pause, find du and v, and come back. Okay, if dv is e to the x, v will be e to the x, and the derivative of cosine x to get to du is going to be negative sine x dx. Okay, now I'm going to hold on to this e to the x sine x that I had before, and I'm going to do my uv minus the integral of v du using this stuff to replace this part of this integral. Okay, so pause and come back to me. Okay, I'm holding on to that negative, so I'm going to do minus uv plus the integral of v du actually. So I'm going to do minus uv, so minus e to the x cosine x. Okay, minus a negative, which is going to give me my plus the integral of v du, so e to the x times sine x dx, so plus the integral of e to the x sine x dx. Okay, now if you notice what happened, my integral is no better and no worse. It pretty much stayed the same, and a little disappointingly, I am back to my original integral. Okay, so I want you to think about what we did initially to do these to come up with a formula and how we were moving integrals around, and I want you to think about, I have a sign mistake someplace in here. Okay, the sign mistake was right. I had 3 negatives. I had 1 negative, 2 negatives, and then the fact that I'm doing minus the integral of v du, so I actually had 3 negatives. There should have been a minus here. Okay, so I want you guys, I'm running out of time again. I'm going to put up an answer, but just think about algebraically how you can manipulate this, knowing where this came from, that this integral is equal to all this stuff over here, and see if you can solve for this integral. Okay, and we'll go over it in class tomorrow.